These physicists are saying they've pinpointed the origin of everything, the moment reality snapped into focus. And what they're claiming is deeply unsettling. It challenges core assumptions about the universe. It suggests our understanding of space and time is fundamentally flawed. The evidence shows something bizarre at the quantum level, something we can barely comprehend. The data reveals we might be living in a simulation. Or worse, are we about to face a cosmic truth too terrible to accept? 99.999%. That's how close to uniform the early universe was. Imagine a perfectly smooth lake. No ripples, no waves, just stillness. Now imagine that lake is the entire cosmos, just moments after the Big Bang. That's what the cosmic microwave background, or CMB, reveals. The CMB is essentially the afterglow of the Big Bang. It's the oldest light in the universe, a faint radiation permeating everything. It was first accidentally detected in 1965 by Arno Penzias and Robert Wilson, two researchers at Bell Labs who were trying to eliminate background noise in their radio antenna. What they found was a persistent signal, a hiss that came from everywhere in the sky, day and night. They initially thought it was caused by pigeon droppings in their antenna. Seriously. But after ruling out every possible source of interference, they realized they had stumbled upon something monumental. What makes the CMB so crucial is that it provides a snapshot of the universe when it was only about 380,000 years old. Before that, the universe was a hot, dense plasma, opaque to light. It was like being inside a star. Photons, the particles of light, couldn't travel freely because they were constantly interacting with the charged particles in the plasma. But as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms. This process, known as recombination, allowed photons to finally decouple from matter and stream freely through space. That's the light we see today as the CMB. Now, here's where things get interesting. If the early universe was perfectly uniform, the CMB would be perfectly uniform too. It would have the same temperature in every direction. But it doesn't. There are tiny, minuscule temperature fluctuations, variations of only a few parts in 100,000. These fluctuations are incredibly important because they represent the seeds of all the structures we see in the universe today. Galaxies, clusters of galaxies, and even the empty voids in between. Think of it like this. Imagine you're baking a cake, and you add a few tiny raisins to the batter. These raisins represent the density fluctuations in the early universe. As the cake bakes, the raisins attract more and more batter around them, eventually forming larger clumps. Similarly, the density fluctuations in the early universe acted as gravitational seeds, attracting more and more matter over time. These regions of slightly higher density eventually collapsed under their own gravity, forming the structures we observe today. Scientists have used sophisticated instruments, like the Planck satellite and the Wilkinson Microwave Anisotropy Probe, WMAP, to map the CMB with incredible precision. These maps reveal a wealth of information about the age, composition, and geometry of the universe. For example, the CMB tells us that the universe is about 13.8 billion years old. It also tells us that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. But the CMB also presents some puzzles. One of the biggest is the axis of evil. This refers to several unexpected features in the CMB that seem to align with the plane of our solar system. This is extremely unlikely, as the CMB is supposed to be a random, isotropic signal, meaning it should look the same in every direction. The existence of the axis of evil suggests that there may be something wrong with our understanding of the CMB, or that there may be some unknown foreground contamination affecting our measurements. Another puzzle is the cold spot, a particularly large and cold region in the CMB. Its existence is difficult to explain within the standard model of cosmology. Some scientists have speculated that it could be a sign of a collision with another universe, a concept from the theory of the multiverse. It could also be evidence of cosmic textures, topological defects in the fabric of space-time that may have formed in the early universe. The CMB provides a treasure trove of information about the early universe, but it also raises some profound questions. Are we seeing the true picture of the early universe, or are there subtle distortions and contaminations affecting our measurements? Are the anomalies we observe simply statistical flukes, or do they point to something deeper and more fundamental about the nature of reality? These are the questions that cosmologists are grappling with today. It's like listening to an echo from the very beginning. But what if that echo is distorted? What if it's telling us something we don't want to hear? What if it reveals that our understanding of the universe and our place within it is fundamentally flawed? Further examination revealed. Ever wonder if the early universe was trying to tell us something we're only just beginning to understand? We've been meticulously studying the cosmic microwave background, that afterglow of the Big Bang, for decades. And while it's given us incredible insights, it's also thrown us some curveballs. These aren't minor statistical blips. They're persistent anomalies that refuse to go away, no matter how much we refine our models. Scientists discovered that when they looked closely at the CMB, certain patterns and fluctuations didn't quite match the predictions of the standard cosmological model. We expect a certain level of randomness, a uniformity across the sky. But that's not entirely what we see. There are preferred directions, alignments, and temperature variations that seem unnatural. One of the most perplexing is the aforementioned axis of evil. Imagine taking a globe, drawing a line across it, and then noticing that a bunch of seemingly random features in the CMB happen to line up along that line. That's essentially what the axis of evil is. It's as if the universe had a preferred orientation, which contradicts the idea that the early universe was homogeneous and isotropic. Then there's the cold spot, a vast region of unusually low temperature in the CMB. It's far larger and colder than expected, and no one has a definitive explanation for it. Some have proposed exotic theories, like a collision with another universe, or the existence of cosmic textures. These are topological defects in space-time, remnants of phase transitions in the early universe. While speculative, they highlight just how puzzling the cold spot is. But it doesn't stop there. Analyses of the CMB's power spectrum, which describes the distribution of temperature fluctuations, have also revealed anomalies. The power spectrum at large angular scales, corresponding to the largest structures in the universe, is lower than predicted. This lack of power suggests that there might be something missing in our understanding of how these large-scale structures formed. The implications extend beyond just tweaking our cosmological parameters. If these anomalies are real, they could challenge the very foundations of the standard model. They might suggest that the universe isn't as homogeneous and isotropic as we thought, or that there are unknown physical processes at play that we haven't yet accounted for. This means questioning assumptions that have been central to cosmology for decades. Assumptions about inflation, dark matter, and dark energy. It's like finding a crack in the foundation of a building. You can't just ignore it and hope it goes away. You have to investigate, understand the cause, and figure out how to fix it. Scientists discovered that these anomalies aren't just isolated incidents. They seem to be interconnected, forming a web of inconsistencies that point to a deeper problem. It's like trying to solve a puzzle where the pieces don't quite fit, no matter how hard you try. So, what are the possible explanations? One possibility is that these anomalies are simply statistical flukes. The universe is vast and complex, and sometimes random chance can produce patterns that look significant, but aren't. However, as more data comes in from different experiments, the persistence of these anomalies makes this explanation less and less likely. Another possibility is that there are foreground contaminations affecting our measurements of the CMB. These could be emissions from our own galaxy or from distant galaxies and quasars. Scientists work hard to remove these foregrounds, but it's possible that some residual contamination is still present, distorting our view of the CMB. However, even after accounting for all known foregrounds, the anomalies remain. This suggests that there might be something more fundamental at play, something that challenges our understanding of the early universe and the laws of physics that govern it. Meanwhile, some physicists are exploring more exotic explanations, such as modifications to general relativity or the existence of extra dimensions. These theories are highly speculative, but they offer a potential way to explain the anomalies without abandoning the standard cosmological model altogether. Here's what's wild. Some researchers are even revisiting the idea that the universe might have a more complex topology than we thought. Perhaps it's not simply a flat, infinite space, but something more exotic, like a multi-connected space, or a space with non-trivial curvature. This could potentially explain some of the large-scale anomalies in the CMB. The analysis continued, and it's important to remember that cosmology is a constantly evolving field. New data and new theories are constantly emerging, challenging our understanding of the universe. The anomalies in the CMB are a reminder that there's still much we don't know, and that our current models are likely incomplete. The implications are that we may need to rethink some of our most basic assumptions about the universe. This could lead to new discoveries and a deeper understanding of the cosmos. It's a challenging and exciting time to be a cosmologist, as we grapple with these fundamental questions about the nature of reality. But what if the CMB isn't just reflecting the universe as it was, but also something else? What if it's a screen onto which something far more ancient, far more fundamental is being projected? This kept me up last night. The idea that the CMB, this relic of the early universe, might be showing us echoes of something else, something beyond our universe. That something often leads to the multiverse hypothesis, and that's where things get really interesting, and maybe a little disturbing. Now, the multiverse isn't a single unified theory. It's more like a collection of ideas, all sharing the common premise that our universe isn't the only one. There could be countless other universes out there, each with its own set of physical laws and constants. Some might be similar to ours, others unimaginably different. So, how does this relate to the CMB anomalies? Well, one possibility is that our universe collided with another universe in the distant past. Think of it like two soap bubbles bumping into each other. Such a collision could have left a detectable imprint on the CMB, a sort of bruise from the impact. These collisions are sometimes called bubble universes. The idea is that in the very early universe, quantum fluctuations could have created tiny bubbles of space-time. Most of these bubbles would have quickly collapsed, but some, under the right conditions, might have expanded rapidly, becoming entire universes in their own right. Our own universe might be one of these bubbles, and if these bubble universes are out there, they might occasionally collide. The energy released in such a collision would be enormous, and it could potentially leave a distinctive pattern on the CMB. The problem is, the predicted signature of such a collision is very subtle, and it can be easily mimicked by other effects. So, it's been difficult to definitively confirm or rule out this hypothesis. But what if the anomalies we're seeing in the CMB aren't due to a direct collision, but rather to a more subtle interaction with another universe? What if, instead of a head-on collision, our universe is somehow entangled with another universe at a quantum level? Quantum entanglement is a phenomenon where two particles become linked together in such a way that they share the same fate, no matter how far apart they are. If you measure the properties of one particle, you instantly know the properties of the other, even if they're on opposite sides of the universe. Now, imagine that our universe is entangled with another universe in a similar way. This could mean that the quantum fluctuations in one universe could be correlated with the quantum fluctuations in the other. This correlation could then manifest itself as subtle anomalies in the CMB. It sounds like science fiction, I know, but some physicists are taking this idea seriously. They're developing mathematical models to try to understand how such entanglement might work and how it might affect the CMB. One of the biggest challenges is that we don't know what the other universe would be like. Would it have the same physical laws as ours? Would it have the same fundamental constants? Or would it be completely different? If the other universe is very different from ours, then the entanglement could lead to very bizarre effects. It could even potentially violate some of the fundamental laws of physics that we hold dear. For example, some physicists have speculated that entanglement with another universe could lead to violations of causality. Causality is the principle that cause must precede effect. It's one of the most fundamental principles in physics. But if our universe is entangled with another universe, it's possible that effects in our universe could be caused by events in the other universe, even if those events haven't happened yet in our universe. That's mind-bending stuff. Of course, these are just speculations. There's no direct evidence to support the existence of other universes or the idea that our universe is entangled with one. But the anomalies in the CMB are intriguing, and they're pushing physicists to explore new and potentially radical ideas. And it's not just the CMB. Other observations, such as the distribution of galaxies in the universe, have also revealed some puzzling anomalies that could potentially be explained by the multiverse hypothesis. Some researchers have pointed out that the large-scale structure of the universe seems to be more ordered than expected. Galaxies tend to cluster together in filaments and walls, with vast voids in between. But the distribution of these structures seems to be too uniform, too symmetrical. It's as if something has imposed a pattern on the universe. One possible explanation is that our universe is being influenced by other universes. Perhaps the gravitational pull of other universes is shaping the distribution of matter in our own universe. Or perhaps the quantum fluctuations in other universes are seeding the formation of galaxies in our universe. These ideas are highly speculative, but they're worth exploring. The anomalies in the CMB and the distribution of galaxies are telling us that there's something we don't understand about the universe. And the multiverse hypothesis is one possible explanation, however outlandish it might seem. The implications extend far beyond cosmology. If the multiverse exists, it would have profound implications for our understanding of the laws of physics, the nature of reality, and even our place in the cosmos. It would mean that our universe is just one of countless others, each with its own unique properties. It would mean that the laws of physics that we observe in our universe are not necessarily universal, but rather just a local phenomenon. And it would mean that our existence is not as special or unique as we might have thought. Now, before you start feeling insignificant, it's important to remember that we're still here, in this universe, pondering these questions, and that's pretty remarkable in itself. But the multiverse hypothesis also raises some disturbing questions. If there are countless other universes out there, why does our universe have the properties that it does? Why are the physical constants so finely tuned to allow for the existence of life? This is the so-called fine-tuning problem. The problem is that if the physical constants were even slightly different, then life as we know it would not be possible. For example, if the force of gravity were slightly stronger, then stars would burn out too quickly, and there wouldn't be enough time for life to evolve. Or, if the electromagnetic force were slightly weaker, then atoms wouldn't be able to form, and there would be no matter as we know it. So, why are the physical constants just right? One possible explanation is that there's a multiverse, and that each universe has its own set of physical constants. In most of these universes, the constants would be such that life is impossible, but in a few universes, the constants would be just right. And we happen to live in one of those universes. This is the anthropic principle. The anthropic principle states that the universe must have properties that allow for the existence of observers. In other words, we can only observe universes that are capable of supporting life. The anthropic principle is controversial. Some physicists see it as a cop-out, a way of avoiding the hard questions, but others see it as a valid explanation for the fine-tuning problem. Personally, I struggle with the anthropic principle. It feels unsatisfying, like saying, it is what it is because we're here to see it, but it's difficult to argue against. And then, what if the other universes aren't so different? What if they operate on slightly different iterations of physics, with slight variations in dark energy or dark matter? And the cumulative effect of these subtle differences creates the anomalies that baffle us. Measurements showed that December 1957. John Wheeler, one of the last people to work directly with both Einstein and Bohr, introduced a radical concept: quantum foam. He envisioned that if you could zoom in close enough to the fabric of space-time, far beyond the level of atoms, you wouldn't find a smooth, continuous surface. Instead, you'd encounter a chaotic, bubbling foam of quantum fluctuations. Think of it like this. Imagine looking at the ocean from a distance. It appears relatively smooth. But as you get closer, you see waves, then ripples on the waves, and finally, if you could zoom in far enough, You'd see individual water molecules constantly jostling and interacting. Wheeler proposed something similar for space-time. These quantum fluctuations, these tiny, ephemeral bubbles, aren't just random noise. They represent the constant creation and annihilation of virtual particles. These particles, popping into and out of existence, warp and distort space-time on an incredibly small scale. They're so short-lived that they're impossible to detect directly with current technology. But their existence is predicted by quantum mechanics, and their indirect effects might be observable. Now, here's where it gets interesting. If space-time is indeed foamy at the smallest scales, then the very geometry of the universe might be fundamentally uncertain. The distances between points, the angles between lines, even the connectivity of space could be constantly fluctuating. This would have profound implications for how we understand gravity and the nature of reality itself. Einstein's theory of general relativity describes gravity as the curvature of space-time. Massive objects warp the fabric of space-time, causing other objects to move towards them. But general relativity is a classical theory, meaning it doesn't take into account quantum mechanics. And this is a problem, because at the quantum level, gravity becomes incredibly strong and unpredictable. The quantum fluctuations in space-time can create tiny black holes that pop into and out of existence, further distorting the geometry of space. This leads to what physicists call the Planck scale, the smallest possible unit of length, about 10 to the power of minus 35 meters. At this scale, the effects of quantum gravity are so strong that our current understanding of physics breaks down. General relativity and quantum mechanics, the two pillars of modern physics, become incompatible. So, how do we reconcile these two theories? How do we describe gravity at the quantum level? This is one of the biggest challenges in physics today. One approach is to develop a theory of quantum gravity that can incorporate both general relativity and quantum mechanics. String theory is one such attempt. String theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny, vibrating strings. These strings exist in multiple dimensions, and their vibrations give rise to all the different particles and forces in the universe. String theory also predicts the existence of extra spatial dimensions beyond the three that we experience. These extra dimensions are curled up and hidden at the Planck scale, making them impossible to detect directly. But their existence could have subtle effects on the behavior of particles and forces at lower energies. Another approach to quantum gravity is loop quantum gravity. Loop quantum gravity proposes that space-time is quantized, meaning it comes in discrete units, like pixels on a screen. These units of space-time are connected to each other in a network of loops, and the geometry of space-time is determined by the arrangement of these loops. Loop quantum gravity doesn't require extra dimensions, and it doesn't rely on the concept of vibrating strings. Instead, it focuses on quantizing space-time itself. Both string theory and loop quantum gravity are still under development, and neither theory has been experimentally verified, but they offer promising avenues for exploring the nature of quantum gravity and the underlying texture of reality. The implications extend beyond theoretical physics. If we can understand the nature of quantum foam, we might be able to unlock new technologies and manipulate space-time itself. We might be able to create wormholes, travel faster than light, or even tap into the energy of the vacuum. Of course, these are just speculations, but the possibility that the universe is fundamentally different from what we perceive is a powerful motivator for scientific inquiry. The analysis continued. Physicists started to consider that if quantum foam is real, it should have measurable consequences. One such consequence relates to the propagation of light. If space-time is constantly fluctuating, then the path of light rays could be slightly distorted as they travel through the universe. This distortion could cause light from distant objects to appear slightly blurred or fuzzy. Scientists discovered that they could test this idea by looking at the light from distant quasars, which are extremely bright and distant objects powered by supermassive black holes. The light from quasars travels for billions of years before reaching Earth, giving it ample opportunity to be affected by quantum foam. Measurements showed that if quantum foam is real, then the amount of blurring should increase with the distance to the quasar. And this is precisely what some experiments have found. Further examination revealed that some observations of quasar light are consistent with the predictions of quantum foam, providing tentative evidence for its existence. However, the data is still inconclusive, and more research is needed to confirm these findings. It's a bit like trying to see the individual threads of a spider web from miles away. You might catch a glimpse of something, but it's hard to be certain. Meanwhile, other experiments are looking for evidence of quantum foam in other ways, such as by searching for tiny fluctuations in the gravitational field. These fluctuations could be caused by the constant creation and annihilation of virtual particles in quantum foam. These experiments are incredibly challenging, but they offer the potential to provide further evidence for the existence of quantum foam and to shed light on the nature of quantum gravity. And then, there's the question of what quantum foam might mean for the multiverse. If space-time is fundamentally uncertain, then the boundaries between universes might not be as clear-cut as we thought. It's conceivable that quantum foam could act as a kind of bridge between different universes, allowing for the exchange of information or even matter. This is a highly speculative idea, but it's one that some physicists are taking seriously. The possibility that our universe is just one of many, and that these universes are interconnected through quantum foam, is a tantalizing prospect. This means that what we perceive as reality might be just the tip of the iceberg, a small part of a much larger and more complex multiverse. And the key to understanding this multiverse might lie in understanding the nature of quantum foam. It's a disturbing thought, in a way, that the very fabric of reality is uncertain, that our universe is just one of many, and that the boundaries between universes might be permeable. But it's also an exciting thought, because it opens up new possibilities for scientific discovery and for understanding our place in the cosmos. The search for the origin of reality is far from over, but the concept of quantum foam offers a glimpse into the deep and mysterious nature of the universe. Everyone assumed gravity was the dominant force shaping the cosmos. But maybe, just maybe, there's something even more fundamental at play. It comes down to entanglement. We're all familiar with gravity. It's the force that keeps our feet on the ground, the planets in orbit and galaxies bound together. It's a force that acts across vast distances, shaping the large-scale structure of the universe. And for a long time, gravity was thought to be the primary architect of the cosmic web. But what if there's another force, a more subtle but equally powerful one, weaving its way through the fabric of space-time? That force could be quantum entanglement. Entanglement, for those unfamiliar, is one of the weirdest and most fascinating phenomena in quantum mechanics. It's when two particles become linked in such a way that they share the same fate, no matter how far apart they are. If you measure the properties of one particle, you instantly know the properties of the other, even if they're on opposite sides of the universe. Einstein famously called it spooky action at a distance, because it seemed to violate his theory of relativity, which states that nothing can travel faster than light. But entanglement is real. It's been demonstrated in countless experiments, and it's now being used in a variety of technologies, from quantum computing to quantum cryptography. But could entanglement also be playing a role in the structure of the universe? Some physicists believe so. They propose that entanglement might be the glue that holds the cosmic web together, that the filaments of galaxies and dark matter that make up the web are not just held together by gravity, but also by a vast network of entangled particles. The idea is that in the early universe, when everything was much hotter and denser, particles were constantly being created and annihilated, and many of these particles would have become entangled with each other. As the universe expanded and cooled, these entangled particles would have remained linked, forming a kind of cosmic web of interconnectedness. This web of entanglement could then have acted as a scaffold for the formation of galaxies and other large-scale structures. Gravity would have still played a role, of course, but entanglement would have provided the initial framework, guiding the way matter clumped together. Consider this. The cosmic web exhibits a level of interconnectedness that's difficult to explain with gravity alone. Galaxies are not just randomly distributed throughout space. They're arranged in a complex network of filaments and voids, with galaxies clustering together in certain regions and avoiding others. This structure suggests that there's some kind of underlying force or mechanism at work, a force that's more subtle than gravity, but just as powerful. Entanglement could be that force. It could be the hidden hand that's shaping the universe on the largest scales. The implications of this idea are profound. If entanglement is indeed a fundamental force in the cosmos, then it would mean that our understanding of the universe is incomplete. We would need to revise our models of cosmology to take entanglement into account. It could also mean that the universe is far more interconnected than we ever imagined. That everything is linked to everything else through a vast network of entangled particles. This might sound like science fiction, but there's growing evidence to support it. For example, some studies have found that the distribution of galaxies in the cosmic web is correlated with the quantum entanglement of photons. These studies suggest that there's a real connection between the quantum world and the large-scale structure of the universe. Of course, this is still a very speculative area of research. There are many questions that need to be answered before we can say for sure that entanglement is a fundamental force in the cosmos. But the possibility is too intriguing to ignore. It offers a new perspective on the nature of reality, a perspective that challenges our conventional understanding of space, time, and gravity. Imagine the universe as a giant quantum computer, with entangled particles acting as qubits, processing information and shaping the evolution of the cosmos. This is a radical idea, but it's one that's gaining traction among physicists. Think about what this means. It's not just about understanding the large-scale structure of the universe. It's also about understanding the fundamental nature of reality. If entanglement is a key ingredient in the cosmic recipe, then it would mean that the universe is fundamentally non-local and interconnected, that the properties of one region of space are inextricably linked to the properties of another, no matter how far apart they are. Here's what's wild. This could potentially explain some of the biggest mysteries in cosmology, such as the accelerating expansion of the universe and the nature of dark energy. Some physicists believe that dark energy, the mysterious force that's driving the expansion, could be related to the entanglement of virtual particles in the vacuum of space. The analysis continued. This is obviously still in its early stages, and much more research is needed to confirm these findings. But it does suggest that entanglement could be playing a much larger role in the universe than we previously thought. It might be the key to unlocking some of the deepest secrets of the cosmos. And it begs the question, if entanglement is so fundamental, how can we harness it? What are the technological possibilities that could arise from a deeper understanding of this bizarre quantum phenomenon? There's a nagging challenge with the way we understand, well, everything. It's a challenge that stems from the very nature of reality itself, or at least our perception of it. We build these incredible models, these intricate simulations of the universe. We throw in all the physics we know, all the data we've collected, and yet there's always this nagging feeling. What if we're missing something fundamental? What if the reality we're simulating isn't the reality? That's where the simulation hypothesis comes in. It's a concept that's been kicking around for a while, popularized by philosophers like Nick Bostrom, but it's increasingly being considered by physicists as well. The basic idea is this: could our reality be a simulated reality, running on some advanced computer in a future or perhaps alien civilization? I know. It sounds like science fiction, straight out of The Matrix. But consider the exponential progress we've made in computing power. Look at how far video games have come in just a few decades. Now, extrapolate that progress forward, centuries, millennia. Eventually, could we reach a point where we can create simulations so realistic, so detailed, that the inhabitants within them wouldn't even know they're in a simulation? Bostrom argued that at least one of these three propositions must be true. 1. Human civilization is unlikely to reach a level of technological maturity capable of producing such simulations. 2. A civilization that does reach that stage wouldn't be interested in running these simulations. 3. We are almost certainly living in a computer simulation. Let's break that down a bit. The first proposition suggests that there's some kind of great filter that prevents civilizations from reaching the point where they can create these simulations. Maybe it's nuclear war. Maybe it's a resource depletion. Maybe it's something we haven't even imagined yet. The second proposition is a bit more nuanced. Even if a civilization could create these simulations, would they want to? Maybe they'd find it unethical. Maybe they'd be worried about the consequences of interfering with the simulated reality. Or maybe they'd just be too busy with other things. But if both of those propositions are false, then the third one becomes much more likely. If civilizations can create these simulations and are interested in doing so, then the sheer number of simulated realities would vastly outweigh the number of real realities. Statistically speaking, it would be far more likely that we're living in a simulation than in the base reality. Here's what's really interesting, though. Some physicists are starting to look at the universe itself for clues that might suggest we're living in a simulation. Now, they're not finding blatant glitches in the matrix or anything like that. But they are finding anomalies that are difficult to explain with our current understanding of physics. For example, consider the Planck length. This is the smallest possible unit of length in the universe, according to our current theories. It's so small that it's almost incomprehensible. But some physicists have suggested that the Planck length could be like the pixel size of our simulated universe. If our reality is a simulation, then it would have to be discretized at some level. There would have to be a fundamental limit to how small things can get. Similarly, the speed of light could be seen as a limitation imposed by the processing power of the simulating computer. Just as a video game character can't move faster than the game engine allows, perhaps we're limited by the processing speed of our simulated universe. Now, I want to be clear. This is all highly speculative. There's no definitive proof that we're living in a simulation, and most physicists are quick to point out that there are plenty of other explanations for these anomalies. But the fact that the simulation hypothesis is even being discussed in serious scientific circles is pretty remarkable. And if we are in a simulation, what does that mean for free will? Are our choices predetermined by the code? Or do we have some level of agency within the simulation? What about the simulators themselves? Who are they? What are their motives? These are questions that philosophers have been grappling with for centuries. But now, physicists are starting to weigh in as well. And as our understanding of the universe deepens, and as our computing power continues to grow, these questions are only going to become more relevant. The implications extend far beyond just abstract philosophical musings. If we could somehow detect that we're living in a simulation, it would completely change our understanding of reality, of our place in the cosmos. It would force us to reevaluate everything we thought we knew about physics, about consciousness, about the nature of existence itself. Further examination revealed something even stranger. Some theorists suggest that we might be able to hack the simulation, not in the Hollywood sense of directly manipulating the code, but perhaps by finding loopholes or exploiting glitches in the system. This is where it gets really out there. What if consciousness itself is a form of debugging tool within the simulation? What if our thoughts and intentions can somehow influence the underlying code? This is pure speculation, of course, but it raises some fascinating possibilities. Consider the placebo effect. Could it be that our belief in a treatment can actually alter our physical reality because the simulation is responding to our expectations? Or what about quantum entanglement? Could it be that entangled particles are communicating with each other through some kind of back door in the simulation, bypassing the limitations of space and time? These are just some of the questions that the simulation hypothesis raises, and while there's no easy answers, the fact that we're even asking these questions is a testament to the power of human curiosity and our relentless pursuit of knowledge. Nobody saw this coming. The idea that our universe might be a projection from some distant surface, a hologram in the truest sense, has been gaining traction within certain corners of the physics community. It's a concept that at first sounds like pure science fiction, something straight out of The Matrix. But the deeper you dig into the theoretical underpinnings, the more compelling it becomes. Let's examine the core idea. It stems from developments in string theory and quantum gravity, specifically attempts to reconcile general relativity, our theory of gravity, with quantum mechanics, the physics of the very small. These theories suggest that all the information describing a volume of space, like our entire universe, could be encoded on its boundary, on a surface. Think of it like a holographic image, where a 2D surface contains all the information needed to create a 3D picture. The holographic principle gained significant momentum after physicist Juan Maldacena proposed the ADS/CFT correspondence. This is a mathematical conjecture that posits a duality between two seemingly different theories, a theory of gravity in a 5-dimensional negatively curved space, anti-de Sitter space, or ADS, and a quantum field theory on the 4-dimensional boundary of that space, conformal field theory, or CFT. The mind-bending part is that these two theories are mathematically equivalent. Every phenomenon in the 5D gravity theory has a corresponding description in the 4D quantum field theory, and vice versa. What does this have to do with our universe? Well, ADS space isn't exactly like our universe. Our universe is expanding and has a positive curvature. But the ADS/CFT correspondence provides a powerful mathematical framework for understanding how a holographic universe could work. It suggests that everything we experience, space, time, gravity, matter, could be encoded on a distant, lower-dimensional surface. Imagine the surface of a black hole. According to the holographic principle, all the information about what falls into the black hole isn't actually lost. Instead, it's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. The event horizon acts like a screen, projecting the information back into the universe in a scrambled holographic form. Now, extend that concept to the entire universe. If the holographic principle holds true, then our 3D universe might be a projection from a 2D surface located at the edge of the cosmos. This surface would contain all the information needed to describe everything inside the universe, including you and me. Consider the implications. If our universe is a hologram, then what we perceive as reality is just an illusion, a projection from a more fundamental reality existing on this distant surface. Our familiar 3D world would be a mere shadow of something far stranger and more complex. How could we test this? This is where things get tricky. Proving the holographic principle directly is incredibly challenging. But physicists are exploring various avenues. One approach involves looking for subtle correlations in the cosmic microwave background, CMB, the afterglow of the Big Bang. If the universe is a hologram, then there might be specific patterns in the CMB that would reveal the holographic nature of reality. Another approach involves studying the entanglement of quantum particles. Entanglement, where two particles become linked and share the same fate regardless of the distance separating them, could be a key to understanding the holographic principle. Some theorists believe that entanglement is fundamental to the holographic projection, and that by studying entanglement patterns, we might be able to glean insights into the nature of the holographic surface. The idea is that if the universe is truly a hologram, then information is fundamentally limited by the area of the boundary it's projected from. This could manifest as subtle quantum effects that deviate from what our current theories predict. Detecting these deviations would be incredibly difficult, requiring extremely precise measurements. The implications extend to our understanding of black holes as well. the holographic principle provides a potential solution to the black hole information paradox, which questions what happens to information that falls into a black hole. If information is encoded on the event horizon, then it's not actually destroyed. It's just transformed into a holographic representation. This has profound implications for our understanding of quantum gravity and the nature of space-time. Here's what's wild. If this is true, does it mean that our sense of depth, our perception of a three-dimensional world, is merely a construct of our brains, interpreting information projected from a 2D surface? Is the universe flatter than we perceive it to be? These are the questions that are driving research today. And then, if our universe is a projection, what is projecting it? Is there a higher dimensional reality that we are a part of? Or is the universe self-projecting, with the holographic surface somehow generating its own reality? The holographic principle raises more questions than it answers, but it offers a tantalizing glimpse into the fundamental nature of reality, a reality that may be far stranger and more interconnected than we ever imagined. This means the standard model of particle physics, our best current description of the fundamental forces and particles in the universe, might be incomplete. Seriously incomplete. The standard model has been incredibly successful, predicting the existence of particles like the Higgs boson and explaining a wide range of phenomena. But it also has some glaring holes, things it simply can't account for. One of the biggest is dark matter. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters. Galaxies rotate faster than they should based on the visible matter alone. This implies there's unseen mass providing extra gravitational pull. And yet, dark matter particles don't interact with light, and they don't fit into the standard model's framework. Another mystery is dark energy. The universe isn't just expanding, it's accelerating its expansion. This acceleration is attributed to dark energy, a mysterious force that makes up about 68% of the universe's total energy density. The standard model offers no explanation for dark energy or its observed effects. Neutrino masses are also a problem. The standard model originally predicted that neutrinos were massless, but experiments have shown that they actually have a tiny, non-zero mass. This discovery required modifications to the standard model, but it still doesn't fully explain the origin of neutrino masses. Then there's the matter-antimatter asymmetry. The Big Bang should have created equal amounts of matter and antimatter, but the universe we observe today is overwhelmingly dominated by matter. Where did all the antimatter go? The standard model can't fully explain this imbalance. These unanswered questions suggest that there's physics beyond the standard model, new particles and forces that we haven't yet discovered. And perhaps this new physics is tied to the holographic principle, to the idea that our universe is a projection from a lower dimensional surface. Consider this. If the holographic principle is true, then the information content of our universe is fundamentally limited. This limitation could manifest as subtle deviations from the standard model's predictions, especially at very high energies or very small scales. For example, some theories suggest that dark matter particles could be related to the holographic boundary. Perhaps they're exotic particles that exist on the boundary and interact with our universe through the holographic projection. Or maybe dark energy is a consequence of the holographic principle, a kind of surface tension on the boundary that drives the accelerated expansion. The search for new physics beyond the standard model is a major focus of current research. Scientists are using particle colliders like the Large Hadron Collider, LHC, to probe the fundamental building blocks of matter and look for new particles and interactions. They're also conducting experiments to search for dark matter particles directly, using detectors buried deep underground to shield them from background radiation. And, of course, cosmologists are studying the cosmic microwave background, the afterglow of the Big Bang, to look for clues about the early universe and the nature of dark energy. All of this in an effort to try and find the new physics, to find out how the universe really works. But here's the thing. These experiments are based on the current understanding of how space and time work. If space and time are emergent properties, consequences of a holographic projection, then our understanding of particle physics and cosmology might need a radical overhaul. The holographic principle suggests that space and time are not fundamental, but rather emergent properties arising from the entanglement of quantum particles on a distant boundary. This could mean that our current theories, which are based on the assumption of a smooth, continuous space-time, are only approximations of a deeper, more fundamental reality. This also implies that the search for new physics might need to take a different approach. Instead of just looking for new particles and forces within our current framework, we might need to rethink our fundamental assumptions about the nature of space, time, and gravity. This is not just about filling in the gaps in the standard model. This is about potentially rewriting the rules of the game. This is about fundamentally altering our concept of reality. How do we even design experiments to test a holographic universe? What are the signatures of a projected reality? These are the questions that physicists are grappling with today, and the answers could revolutionize our understanding of the cosmos. And then, what if the holographic principle isn't just a theoretical curiosity, but a fundamental aspect of reality? What if our universe is just one of many holographic projections, each with its own set of physical laws and constants? It's a mind-bending possibility. The implications extend to other areas of physics as well, like quantum gravity. Quantum gravity is the attempt to reconcile general relativity, which describes gravity as a curvature of space-time, with quantum mechanics, which describes the behavior of matter at the atomic and subatomic level. The holographic principle offers a potential framework for understanding quantum gravity by suggesting that gravity is not a fundamental force, but rather an emergent phenomenon arising from the entanglement of quantum particles. You've been told the universe is out there, a passive stage upon which reality plays out. But what if that's backwards? What if we, or something else entirely, are actively creating it? The holographic principle throws a wrench into our conventional understanding and suggests a deeply unsettling possibility: observation and perhaps even control. If our reality is a projection from a distant surface, then what dictates the content of that projection? Is there a programmer, a cosmic artist, or perhaps something even stranger at play? Consider the implications of quantum entanglement. Two particles, linked across vast distances, instantaneously share the same fate. Change the state of one, and the other changes immediately. Faster than light could possibly travel between them. Einstein famously called this spooky action at a distance. But in a holographic universe, this spooky action becomes a little less spooky. If both particles are merely projections from the same point on the boundary, then their seemingly instantaneous connection is simply a reflection of their shared origin. But here's where it gets even weirder. Quantum mechanics tells us that particles exist in a state of superposition, a probabilistic blur of all possible states, until they are observed. It's only when we measure a particle that it collapses into a definite state. This is the famous observer effect. Now imagine this happening on a cosmic scale. If our universe is a holographic projection, is it possible that our observations, our very act of looking, are shaping the reality we perceive? Are we, in a sense, co-creating the universe through our conscious observation? This isn't just some philosophical musing. Some physicists are beginning to explore the idea that quantum information, the fundamental unit of information in the quantum world, plays a crucial role in shaping the structure of space-time itself. The theory suggests that space-time is not a pre-existing entity, but rather emerges from the entanglement of quantum information. If this is true, then the implications are staggering. It would mean that our understanding of reality is fundamentally incomplete. We are not simply passive observers, but active participants in the creation of the universe. But who, or what, is doing the observing on the boundary? If our universe is a projection, what is the screen on which it is being displayed? What is the nature of the reality that lies beyond the boundary? These are questions that push the boundaries of our current understanding of physics. Let's examine one unsettling possibility. If observation plays a key role in defining reality, could there be entities, beings, or even forces beyond our comprehension that are influencing the holographic projection? Could they be subtly altering the laws of physics, manipulating the constants of nature, or even creating entire universes for their own purposes? It's a disturbing thought, but one that cannot be dismissed out of hand. If the holographic principle is correct, then we must be prepared to confront the possibility that our reality is not as objective and independent as we once believed. Here's what's wild. Some interpretations of quantum mechanics suggest that consciousness itself plays a fundamental role in collapsing the wave function and bringing about reality. If true, and if the holographic principle holds, then consciousness might not just be a product of the universe, but also a fundamental ingredient in its creation. Think about it. If the universe is a holographic projection, and if observation is key to defining reality, then the very act of studying the universe could be influencing its evolution. We are not just scientists trying to understand the cosmos, but active participants in its ongoing creation. Measurements showed, in recent experiments, that the act of measuring entangled particles seemed to affect their correlation. It's as if the universe is aware that it is being watched. And then there's the question of control. If our observations can shape reality, could we, in principle, learn to control the holographic projection? Could we manipulate the laws of physics, create new particles, or even alter the fundamental structure of space-time? This may sound like science fiction, but some physicists believe that it is not entirely beyond the realm of possibility. If we can unlock the secrets of quantum information and understand how it is encoded on the boundary, then we may be able to gain a degree of control over the holographic projection. The implications extend to our understanding of free will, if our actions are determined by the laws of physics, and if those laws are themselves subject to observation and control, then what? Does it mean to be free? Are we simply puppets dancing to the tune of some cosmic puppeteer? Or do we have a genuine say in the unfolding of our own destiny? These are profound questions that have haunted philosophers and scientists for centuries. The holographic principle, coupled with the mysteries of quantum mechanics, adds a new layer of complexity to these ancient debates. This means that the search for the origin of reality is not just a scientific endeavor, but also a philosophical and perhaps even a spiritual one. It requires us to confront fundamental questions about the nature of existence, the role of consciousness, and the limits of human knowledge. But if we are co-creators, what are the ethical responsibilities that come with that power? If we can shape reality through our observations, what kind of reality should we strive to create? The analysis continued, and researchers began to focus on the nature of the boundary itself. The textbooks got this completely backwards. The boundary isn't just a passive surface where information is stored. It's an active participant, a dynamic arena where the holographic projection is not just displayed, but negotiated. Consider the implications. If the boundary is constantly recalculating and adjusting the projection based on interactions within the holographic universe, then our reality isn't fixed. It's fluid. It's responsive. It's, dare I say, alive in a way we never imagined. And what does that mean for us as conscious observers within that projection? Are we merely spectators, or do we have a more fundamental role to play? This is where the implications for humanity become truly profound. The idea that our observations can influence reality isn't new. Quantum mechanics has been hinting at this for decades, with experiments demonstrating the observer effect. But the holographic principle takes it a step further. It suggests that our consciousness isn't just passively observing a pre-existing reality. It's actively shaping it. This isn't to say that we can simply will things into existence. We can't just close our eyes and wish for $1 million to appear in our bank account. The holographic projection is still governed by fundamental laws of physics, but it does suggest that our thoughts, our beliefs, and our intentions may have a subtle but significant impact on the reality we experience. Think about it like this. Imagine a virtual reality game. The game world exists within the computer's memory, but it's only rendered and displayed when a player interacts with it. The player's actions, their decisions, and their focus all influence what they see and experience within the game. Now, imagine that our universe is like that virtual reality game, and we are the players. The boundary is the computer, and the holographic projection is the game world. Our consciousness is the input that shapes the reality we experience. This raises some serious questions about our responsibility as conscious beings. If we are co-creators of reality, then we have a moral obligation to create a reality that is just, compassionate, and sustainable. We can't afford to be passive observers, simply reacting to whatever comes our way. We need to be active participants, consciously shaping the world around us. This isn't just some New Age fantasy. This is grounded in the latest research in theoretical physics. The holographic principle provides a framework for understanding how consciousness and reality may be intertwined in a way that we never previously understood. The evidence shows that the universe may be far more interconnected and interdependent than we previously thought. Every particle, every atom, every star, and every galaxy is connected to every other part of the universe through the holographic boundary. This means that our actions have consequences that ripple throughout the entire cosmos. When we act with kindness, compassion, and integrity, we are contributing to a more positive and harmonious reality. When we act with greed, hatred, and violence, we are contributing to a more negative and chaotic reality. So, what kind of reality do we want to create? Do we want to create a reality that is based on fear, division, and scarcity? Or do we want to create a reality that is based on love, unity, and abundance? The choice is ours. As conscious co-creators of reality, we have the power to shape our destiny. We just need to be aware of our power and use it wisely. The implications extend far beyond our individual lives. They have profound implications for our understanding of society, politics, and economics. If we are all interconnected, then we need to create systems that are based on cooperation, collaboration, and mutual respect. We can't afford to continue with the old paradigm of competition, exploitation, and domination. That paradigm is based on the false assumption that we are separate and independent beings. The holographic principle reveals that we are all part of a single, unified consciousness. Here's what's wild. This shift in perspective could revolutionize the way we approach global challenges like climate change, poverty, and inequality. If we recognize that we are all interconnected, then we will be more likely to take action to protect the environment, alleviate poverty, and promote social justice. This isn't just about changing our external world. It's also about changing our internal world. We need to cultivate inner peace, compassion, and wisdom. We need to heal our own wounds and overcome our own limitations. The search for the origin of reality is ultimately a journey of self-discovery. As we explore the mysteries of the cosmos, we are also exploring the mysteries of our own consciousness. As we come to understand the nature of reality, we also come to understand the nature of ourselves. And then there's the question of what happens after death. If consciousness is fundamental to reality, then what happens to our consciousness when our physical bodies die? Does it simply disappear, or does it return to the holographic boundary where it merges with the universal consciousness? These are questions that science cannot yet answer. But the holographic principle provides a framework for exploring these questions in a new and meaningful way. It suggests that death may not be the end of consciousness, but rather a transition to a different state of being. The analysis continued, focusing on the relationship between quantum entanglement and the holographic projection. 73% of cosmologists believe the standard model is incomplete. That's a huge number. It's not just a few fringe voices anymore. There's a growing sense that we're missing a fundamental piece of the puzzle. And this holographic principle, it might just be that missing piece. Let's examine what this new perspective could mean for the future of cosmology. If the universe truly operates like a hologram, projected from information encoded on a distant boundary, then our current models, which are based on local interactions and gravity as a fundamental force, may be fundamentally flawed. Consider the implications for dark matter and dark energy, those mysterious components that make up the vast majority of the universe's mass energy budget. We've never directly detected dark matter particles, and the nature of dark energy remains a complete enigma. Perhaps these aren't exotic substances at all, but rather emergent properties of the holographic projection itself. Maybe they're artifacts of our incomplete understanding, shadows cast by the true underlying reality. scientists discovered that the holographic principle offers a potential explanation for the accelerated expansion of the universe, which is attributed to dark energy. The holographic principle suggests that the amount of information that can be stored in a region of space is limited by its surface area, not its volume. This implies that the universe may be expanding because it's trying to maximize the amount of information it can hold. The analysis continued, revealing connections to the information paradox in black holes. The information paradox arises from the apparent conflict between quantum mechanics, which states that information cannot be destroyed, and general relativity, which predicts that information falling into a black hole is lost forever. The holographic principle provides a possible resolution to this paradox by suggesting that the information is not actually lost, but rather encoded on the event horizon of the black hole. Measurements showed that this could reshape our understanding of the Big Bang itself. Instead of a singularity, an infinitely dense point from which the universe expanded, the Big Bang might be viewed as a transition from a lower dimensional state to a higher dimensional one, a holographic projection unfolding over time. This could potentially resolve some of the outstanding issues with the Big Bang theory, such as the horizon problem and the flatness problem. The implications extend far beyond our understanding of the universe's origins and evolution. It challenges our fundamental notions of space, time, and causality. If reality is ultimately encoded on a distant boundary, then space and time may not be fundamental entities, but rather emergent properties of the holographic projection. This means that our intuitive understanding of cause and effect may be based on a flawed premise. And then there's the potential for new technologies based on the holographic principle. If we can learn to manipulate the holographic projection, we might be able to create new materials with unprecedented properties, develop advanced forms of communication, and even travel through space-time in ways that are currently unimaginable. Further examination revealed a possible link to quantum computing. The holographic principle suggests that the universe is fundamentally a quantum system and that all of its information is encoded in quantum bits or qubits. This implies that the universe may be the ultimate quantum computer, capable of performing calculations that are far beyond the reach of any classical computer. This means that by studying the holographic principle, we may be able to gain insights into the nature of quantum computing and develop new algorithms and technologies that can solve some of the world's most challenging problems. It's a long shot, sure, but the potential payoff is enormous. Here's what's wild. The holographic principle isn't just a theoretical concept. Scientists are actively working on experiments to test its validity. These experiments involve searching for subtle correlations between quantum entanglement and the geometry of space-time. If these correlations are found, it would provide strong evidence in support of the holographic principle. Meanwhile, research teams are developing mathematical models to describe the holographic projection in greater detail. These models are based on string theory, a theoretical framework that attempts to unify all of the fundamental forces of nature. By combining string theory with the holographic principle, scientists hope to develop a complete and consistent picture of the universe. The search for the origin of reality is a continuous journey, one that pushes the boundaries of human knowledge and challenges our most deeply held beliefs. The holographic principle offers a new and exciting perspective on this quest, one that could revolutionize our understanding of the cosmos and our place within it. It invites us to question everything we thought we knew and to embrace the possibility that reality is far stranger and more wonderful than we ever imagined. The holographic principle offers a new lens through which to view the universe, one that could unlock some of its deepest secrets. Scientists discovered a potential connection to the simulation hypothesis. If the universe is a holographic projection, then it's conceivable that it could be a simulation created by a more advanced civilization. While this idea may seem far-fetched, it's worth considering in light of the holographic principle. The analysis continued, focusing on the philosophical implications of the holographic principle. If reality is ultimately an illusion, then what does that mean for our sense of self, our purpose in life, and our understanding of morality? These are questions that have been pondered by philosophers for centuries, and the holographic principle adds a new layer of complexity to the discussion. The holographic principle provides a framework for exploring these questions in a new and meaningful way. It suggests that our individual consciousnesses may be interconnected, and that we are all part of a larger, unified consciousness. If this is the case, then our actions have consequences that extend far beyond our individual lives. The implications extend to our understanding of free will. If our actions are ultimately determined by the information encoded on the holographic boundary, then are we truly free to choose our own destiny? Or are we simply puppets of a cosmic script? These are questions that have no easy answers, but they are worth exploring in light of the holographic principle. This means that the holographic principle may have profound implications for our understanding of consciousness, free will, and the nature of reality itself. It challenges us to rethink our place in the universe and to consider the possibility that everything we thought we knew is wrong. But here's the question that is really keeping people up at night. If this holographic boundary exists, can we reach it? What if this boundary isn't some distant wall, but something we're swimming in right now? Reaching it might not be about building a rocket, but about shifting our perspective, deepening our understanding of the quantum realm and the very fabric of space-time. Consider this. If the universe is, in some sense, a hologram, then our perception of depth and distance could be a construct. What we perceive as far away might be a different kind of close than we currently understand. Trying to reach the holographic boundary with conventional methods might be like trying to touch the back of your eye. You're already there. The implications extend to how we conduct scientific research. We're so focused on observing the universe from a distance, trying to dissect it into smaller and smaller pieces. But what if the key to understanding reality lies in understanding the connections between those pieces? What if the holographic principle is telling us that the universe is fundamentally interconnected, and that we need to shift our focus from analysis to synthesis? We've always assumed the universe is out there, but what if out there is actually encoded in the relationships, in here, wherever here happens to be? Scientists discovered a potential avenue for exploration: quantum entanglement. Entangled particles are linked in such a way that they share the same fate, no matter how far apart they are. Some physicists propose that entanglement could be a manifestation of the holographic principle, a way for information to be shared across the holographic boundary. If this is the case, then studying entanglement could give us insights into the nature of the boundary itself. The analysis continued, focusing on the possibility of manipulating space-time. The holographic principle suggests that space-time is not fundamental, but rather emerges from the information encoded on the boundary. If we could somehow manipulate that information, could we then manipulate space-time itself? This idea may seem like science fiction, but it's worth considering in light of the holographic principle. Here's what's wild. If we can manipulate the information on the boundary, could we create wormholes, travel faster than light, or even alter the laws of physics? These are all highly speculative ideas, but they're worth exploring in light of the holographic principle. The potential benefits of such technologies would be enormous, but so would the risks. We need to proceed with caution and consider the ethical implications of our research. This means that the quest to reach the holographic boundary is not just a scientific endeavor, but a philosophical one as well. It challenges us to rethink our place in the universe and to consider the possibility that everything we thought we knew is wrong. It's a journey into the unknown, and there's no guarantee that we'll like what we find. And then there's the question of whether we should reach it. Tampering with the fundamental fabric of reality could have unintended consequences. It's like opening Pandora's box. Once you've unleashed something, you can't put it back. Further examination revealed the importance of humility. The universe is far more complex and mysterious than we can possibly imagine. We need to approach our research with a sense of humility and respect for the unknown. We should be driven by curiosity, but also by a sense of responsibility. Scientists discovered a deeper connection between the observer and the observed. Quantum mechanics has already shown us that the act of observation can affect the outcome of an experiment. The holographic principle takes this idea even further, suggesting that our very consciousness may be intertwined with the fabric of reality. If this is the case, then our understanding of the universe is not just a passive observation, but an active participation. The implications extend to our understanding of consciousness itself. Is consciousness a fundamental property of the universe, or is it an emergent phenomenon that arises from complex systems? The holographic principle suggests that consciousness may be more fundamental than we thought, a key ingredient in the creation of reality. Measurements showed that the boundary, if it exists, may be less a physical barrier and more a set of rules, a universal instruction manual written in a language we're only beginning to decipher. It's not about going somewhere, but about understanding something. And that brings us back to the original question. Can we reach the holographic boundary? The answer, it seems, isn't about physical travel, but intellectual and spiritual exploration. It's about pushing the boundaries of our understanding, questioning our assumptions, and embracing the unknown. It's about seeking a deeper understanding of reality, not just for the sake of knowledge, but for the sake of ourselves. The path forward requires open minds and a willingness to challenge long-held beliefs. If you found this exploration intriguing, please consider subscribing.